There's going to be a quiz on Monday over one-dimensional kinematics. And we'll come back to this in a sec because it's relevant, but just understand it's not going to include the stuff that we've been doing with Vector Solver. It's not going to include stuff that we talk about today, which has to do with like two-dimensional motion and things like that. It will be limited to the kinds of problems that were on the basic kinematics practice problems and the kinematics homework 1. There were a lot of problems on those, and if you did them all and you really understood them and you could do them all again right now, which I suggest that you do outside of class, that you try them again and make sure you still remember how to do them, then you're in good shape. For those of you who wanted a key, I did go through the problems. I did it so fast that I'm not confident in all of my answers. But it'll at least be a start. I know most of them are right, and if you see something that doesn't match up with what you have, if you're looking at the key, let me know. If everything matches, then you're in good shape. If things don't match, don't assume it's you. It might be me. If you check your work and everything seems to look good, then just check in with me and I'll double check my work. The problem is I just don't have time. It's not that I'm slacking, but I don't have time to come up with a detailed key for pretty much any of the assignments that we'll do. So in general, if you have questions about stuff, I'll go over it in class, and so then that sort of serves as a key. But if you hadn't tried one of the problems, like if you just tonight or over the weekend sit down and you try problem number 4 and you're like, my answer doesn't match what's on there, then reach out to me and I'll get back to you. The answers, I put the answers right in the document, so it's not a separate thing. You just go back to that document and you'll see that the answers are there. And the quiz is not going to require you to either solve problems algebraically or get answers using the solver. In fact, you won't be able to use the solver at all. And so I'll talk more about it. We'll have a practice quiz on Friday, and I'll talk more about it then. But basically what you're going to do is do all the physics. You're going to get everything set up, and then you're going to tell me, these are the variables that I have. This is the variable I'm looking for. This is the equation I would use. And if you have the ability and time to do the algebra, great, do the algebra. If you don't, that's okay, because I know that you could use the solver to get it. As an aside, if you don't know how to solve the problems that we've been doing algebraically, if that's out of your skill set, then I'm going to recommend to you that you figure that out. Not for me, but by the time you're a junior in high school, that's basic. Those are all basic algebra problems. And it's, if you don't know how to do it, it's not your fault. And it's not our math teacher's fault either. Like, we went through this blip in the pandemic, and largely what happened was we decided that it was better for kids to not demand that they learn things, because some of them weren't going to be able to, and we didn't want everybody to feel bad. We made a judgment call, and the end result of that has been, for pandemic-related reasons and a whole bunch of other reasons, that there are some of you who can't solve a quadratic equation using a quadratic formula. There are some of you who can't solve, 2 equations for 2 unknowns. Those are all relatively basic algebra skills. I can't teach them to you because I don't have time, and this isn't an algebra class, but you're all smart enough to figure it out. So if that's you, if you're like, I wouldn't know how to solve these, like I wouldn't know how to do the algebra if it fell on me, get on Khan Academy, and they'll show you how to do all of it. You have the brain for it, and it's not your fault, it's not anyone's fault. This isn't a blame game thing. We collectively had to make some really tough decisions. We made the decisions we made. Maybe it would have been worse if we would have said, nope, everybody has to master algebra during the pandemic. Like that might have turned out worse for everyone, who knows? So we just did the best we could. But the end result is, in my physics classes now, somewhere between a third and half of the students can't do algebra. and I'm okay with it, but you might need that skill down the road. So that's just a, word to the wise. And then, so that's coming up on Monday of next week. We'll have a practice quiz on Friday, and the problems that we're doing now are similar to, but more complicated than the ones that will be on the quiz. So the work that we're doing now is actually practice for the quiz, even though the quiz itself is going to be simpler. And there is homework that we do on Friday. That's going to be over the newer stuff, but again, that will give you a chance to kind of practice the same sorts of things that you're doing on the quiz. And then very briefly with the tracker quiz, so I had two pieces of evidence that I was accumulating from the quiz. One was your answers, and so I have all the sheets with the numbers on them. The other thing is I was watching you do your work with security, and so I could see what you were doing and how you were doing it. And the take home is some of you aren't quite there yet. You haven't figured out how to use Tracker to find accelerations and velocities at various times. And so I was talking with a couple students this morning because I think my life would be easier if I took a page from the book of Buchanan and was just like, I don't care, I'm posting these grades and you can deal with the fallout. But that's hard for me. It's hard for me because first of all, I don't like it when you're not happy. That just bothers me. I don't want you to not be happy. So it's just something about me personally. The other thing is that very typically, if there's a rough quiz or test, what will happen is that I'll get a flood of communication from students and parents. And some of it is, it's very focused on my student, this student, I wasn't prepared and it's your fault. And I shouldn't care about that either, but I do. I don't want to be seen as a barrier to people's learning. I don't want it to be my fault. And so there's generally, when there's a rough test or a quiz, there's a bailout opportunity. So here's your bailout opportunity. First of all, if you didn't get a score in Canvas, then you didn't get an 80% or better. Everybody who I looked at their work and saw that it was at least 80%, I put the score in. If yours is blank, that means you got no more than 70% on the quiz. And that means that your score, when I do put it in, is going to be no more than 80%. You're officially in retake territory already if your score hasn't been posted. I want to talk to you today because I want to show you, I'll talk to you at lunch, I'm going to show you a couple of things that I think will be helpful, give you a chance to prepare before you do a retake. When you come in for the retake, I want you to know how to do it. And I'm going to tell you what to do and explain what I think went wrong with at least some of you. And then, and just a couple of caveats, and then we'll move on. The first is, it may be that some of you who didn't see a score, you actually do know what you're doing. It may be that something got lost in translation. Maybe your numbers were off enough from mine that it looked to me like you didn't know what you were doing, but it might have been something really basic, like maybe you accidentally made your calibration stick too long, or when you made the calibration stick, it turned out you changed it to 0.75 meters, but you didn't mean to. It might have been something like that, where you know how to use Tracker, you know how to get the information. A one-time thing went wrong, and that's no big deal. So if that's the case, we'll figure that out. And then the other thing is, I do understand that some of you might be otherwise occupied at lunch today. So what I'll say is, if you have an appointment, a doctor's appointment, or if you have something scheduled with another teacher or an administrator or a coach, those are things that you should go to. And so if that's the case, if you can't make it, then I want you to talk to me during class today. We'll make a plan for another time. But do it today during class so that we touch base. And then if you are normally go out to lunch with your friends, or you have a club meeting, that is a lower priority than dealing with this quiz. So if that's where you are, I want you here. And if I don't see you during lunch today, and I don't talk to you during class today, then I'm going to put your score in at the end of the day today, whatever it was. So it might be a 7, it might be a 1. There were a couple of zeros, so it might be a 0. And that's gonna be a big hit to your grade. So make sure you're either here for lunch or you talk to me, so that we have a plan for how to approach a retake. All right, and that's that. I'm not gonna talk any more about that now. You're welcome to check in with me during class to make a plan for an individual meeting. Otherwise, I'll talk to you at lunch. Okay, so let's move on to bigger and better and more physics-related stuff, which is two-dimensional motion and vectors. So here's where we left off. We were talking about these vector components, and I'm not gonna write anything down, but just to kind of very quickly run through it. I want to make sure that that you remember that the deal was that when we're looking at vector components for an actual quantity, those components are not real, but it turns out that they are mathematically equivalent to the original quantity. So if something has a velocity in this direction of magnitude whatever 10, we can mathematically turn that into any number of imaginary vector quantities, so long as when they're all added together using vector math, they are mathematically equivalent to the original vector. And those are called components. In physics, the most useful thing to do is to take a vector quantity and break it into two components that are at right angles to each other. Because of physics magic, motion is independent at right angles. So things that are happening to an object that might affect its left to right motion will not affect or change at all its up and down motion. That works in 3 dimensions as well. So in typical 3-dimensional space, we think about a horizontal, a vertical, and some sort of a depth axis. Anything that is occurring only along one of those axes will not affect the other 2. And that allows us to take a problem that has 2 dimensions of motion, like a curved path, and think about it as 2 separate single dimensions. We're taking one problem that we can't solve and breaking it into 2 problems that we can solve. The 2 problems that we solved are working with quantities that don't fully describe the motion of the object, but when we put them together, they do. And so typically what we're going to do is have a quantity and we'll be like, oh, we can't deal with this one. Let's break it into components, and we'll have one component along one dimension. The other component will be at a 90-degree angle to that dimension. And then sometimes what we end up with is components, but what we want to know is what's the real value. Like we might know that, there's a football, and when it goes over the goalpost, the horizontal part of its velocity is 4 meters per second. The vertical part of its velocity is 1 meter per second, but we want to know how fast it's actually going and what direction it's moving in. And we can do that as well. Both of those processes, taking a vector quantity and breaking it into components, or taking vector components and putting them back together, are things that you've done before in math. Breaking vectors into components involves using some trig. It's related to the sine and cosine of angles, which I no longer have written up there, but there was we can talk about it later. You're gonna need to know some stuff about it, but you don't right now. But it's just using a little bit of trigonometry. And then taking components and putting them back together, there's a little bit of trigonometry involved in finding the angle, but it's also just the quadratic equation, or not the quadratic equation, but the Pythagorean theorem. A squared plus b squared equals c squared. So it's relatively straightforward math, but I've made the vector solver because that math is tedious. And so using the vector solver is a pretty reliable way of taking a vector component, or a vector quantity, breaking it into components, or taking components and putting them back together. And you'll see examples of that today. So here's the new stuff. When we use these 2-dimensional vector quantities in physics, it turns out that we have a few extra things that we need to think about anytime we're solving problems. And this is built into that little algorithm that I told you about to solve kinematics problems. But we're also going to use this when we start talking about forces and when we're talking about momentum. And so we'll be using these techniques for everything, not just kinematics. But the first thing that we have to do is we have to think about where do we want our x and y axes to be located? Like how do we want them to look? And for now, they're always going to look like this, because the two-dimensional motion that we're starting with is going to be projectile motion. Projectile motion is when you have an object that is in free fall, but also moving horizontally at the same time. When that's the case, its acceleration is straight down towards the ground at 10 meters per second squared, and its horizontal motion will have no acceleration. So whatever initial speed it has, left to right or right to left, it will just maintain that speed the entire time that it's moving. And because projectile motion is accelerated straight toward the ground, it makes sense for one of our axes to be straight toward the ground. And that'll be our y-axis. Because one of our axes is straight toward the ground, the other one has to be at a 90-degree angle, which means it's parallel to the ground. So this will be the axis that we use for all of the projectile motion problems. But sometimes things aren't in free fall. Sometimes things are on a flat plane, right? Like something on the ground can be accelerating. And if that's the case, then there is no free fall component, and we can angle our axes in different ways. Other times, like this is going to be sort of the classic problem where we do this. We have an object where its motion is parallel to the surface of a tilted ramp. Its acceleration is in the direction of its motion. And in that case, it turns out it's easier to solve the problem if we tilt our reference frame so that one of the axes, usually we say it's the x-axis, is parallel to the surface of the ramp and the other is perpendicular. We'll use a tilted reference frame for a bunch of other things too. Anytime you have motion that's easier to deal with a tilted reference frame, we'll do it. You don't have to do this, but it's way easier. You have to do a lot less math and a lot less calculations. Conceptually, it's a little tricky, but overall, it ends up being easier to deal with. So you have to do this first, and that's built into the kinematic solver, because that first step says, tell me which are the positive directions and where's 0, 0. So that would be essentially saying, for like a problem like this, if it were, a football being kicked off the ground, which you'll see shortly, that is going to involve saying, I'm going to say to the right is positive and up is positive, and I'm going to say that this location is 0, 0. We've just established our zeros, established our positive directions, and figured out whether our axis is tilted with respect to the ground or not. And in this case, it's not. And then the next thing that you do is you have to think about all the quantities that you're looking at in any kind of a problem or situation. What is the magnitude and what is the direction? And anything that isn't either in one dimension or the other, you need to break into components. And that typically you'll use the solver to do, although sometimes we might have an unknown. And if that's the case, then there's another trick that we'll have to deal with, but you don't have to think about it yet because we're not there. And what happens here is you will be given a quantity and it'll say, like it's, a football is kicked at a certain speed at an angle relative to the ground. And then you'll know, oh, well, if it's kicked at a certain speed at an angle relative to the ground, then it's moving initially diagonally up into the air. It's not moving straight up, so its initial velocity isn't purely in the y dimension, and it's not just moving to the left or the right, so its velocity isn't purely in the x direction either. Its velocity is at an angle to both of our axes, which means to use it, we need to figure out how much of that quantity is vertical and how much is horizontal. When we start looking at motion that uses a tilted reference frame, it's the same thing. If we have a block that's accelerating down a ramp at 2 meters per second squared, and we decide that that's our positive direction, then we may need to find some other quantities that are sort of at angles to those. So maybe something might be like pushing down on the block at this angle. That's a really weird angle for something to be pushing, but we can think of that as having one part that's in our y dimension and one part that's in our x dimension. So we're gonna, anytime we have a quantity that doesn't match up with one or the other of our dimensions, that's when we use the solver to break it into components, or you can use trig, whatever's easier for you. And then, this is just for kinematics, then we go back to our algorithm and we just solve the equations that we get. We're gonna have two sets, one for our x-axis, one for our y-axis. For now, that's gonna be vertical and horizontal. But down the road, it might be parallel and perpendicular to the surface of a ramp. And then sometimes, depending on the problem, we might need to use the solver to put some components back together to come up with some sort of an overall value. It's not always, but sometimes. Okay. So the simplest kind of problem to solve in two-dimensional kinematics is projectile motion, where you have something that is launched or kicked or thrown with a known speed from a known height above where it lands. And to make that even simpler, we can say it always lands on the ground. And in that very simple, very specific category of problem, you're always asked the same thing: how far does it go? So if I throw a ball at a 15-degree angle with an initial speed of 5 meters per second from 1.5 meters above the ground, how far will it go before it hits the ground? Or if you have a launcher, we have all sorts of projectile launchers that we're going to use in this classroom. If we set it up, we put it on one of the lab benches, and we tilt it at a 20-degree angle, and we fire it, and we know that it comes out at 4 meters per second, then how far will it go before it hits the ground? That's sort of the prototypical problem. So I'm going to show you a very specific algorithm for solving that kind of problem. We'll practice that first, and then as we move forward, we're going to add to that mix, and eventually we'll be looking at all sorts of variations of 2D kinematics and beyond problems. We might not just be looking for the final horizontal distance of a projectile, we might be looking for something completely different, and the motion might not be free fall, but we'll start with this. So this is a specific algorithm for a very specific kind of problem, but this is the one we're going to start with because it's the easiest. So what we're going to do is predict how far something is going to move horizontally when it's launched at some angle. The angle might be 0, by the way, and when things are launched at a 0-degree angle, they're launched perfectly horizontally. And that's a special case. That's even simpler, and you'll have a chance to solve these problems. When you have a problem like this, you're always going to be given the same information. You'll know how fast the object is moving, including its angle. You'll know the initial velocity. Velocity is a vector quantity, has a magnitude and direction. So if I tell you something is launched at 5 meters per second, that's not the velocity. That's the speed. You need to know the angle to know the velocity, because the velocity includes direction. If I tell you something is launched at a 20-degree angle with a speed of 4 meters per second, now you know the velocity, the direction and the magnitude. You need to know both of those things. And then you need to know the height, and again, technically, this doesn't have to be the height above the ground, because whatever you're launching might not land on the ground, and you'll see that. We're going to, not today, but we will deal with problems where things don't land on the ground. If I had a tennis ball right here, I could throw that tennis ball and have it land in the sink. It doesn't matter how high the tennis ball is above the ground in that case. What matters is how high is the tennis ball above where it ultimately lands in the sink. And that's always the case when we're dealing with projectile motion. It's just that very typically we're aiming for the ground. Very typically, for these very basic problems, the starting problems, what we want to know is how far is it going to go before it hits the ground? And ultimately, we'll add more to that. So to solve this problem, the first thing that you do is you're going to figure out how long it's going to take for that projectile to land on the ground. And there's a bunch of steps to that. Do you have a question, or are you just okay? There's a bunch of steps to that. First of all, remember that the up and down part of that projectile's motion is completely separate from its left to right motion mathematically. In reality, they're not separate. In reality, what you're going to see if I throw a tennis ball, like if I had a tennis ball in this drawer right here, and I were to take it out and throw it, what you're going to see is one tennis ball moving in a parabolic arc from left to right as you're sitting. But from a mathematical perspective, that tennis ball is going to have a horizontal motion that looks like this if we ignore the vertical motion. And it's going to have a vertical motion that looks like this if we ignore the horizontal motion. It's going to go up, and then it's going to go back down. If you were all standing behind me and you closed one eye, so you lost like your stereo vision, and it was kind of dim, and I didn't throw it very far, if I threw it directly away from you, what you would see is ball goes up, ball comes down. It's moving away from you at the same time, but you wouldn't really see that. And if you were above me looking down, you would see ball goes this way. And that's it. It would also be coming up toward you, but you wouldn't really see that because it would be, in a plane that you wouldn't be able to see very clearly. And so what we're going to do is first just think about the vertical part of the motion of the ball or of the projectile. So knowing that the vertical motion and horizontal motion are independent, what determines how long it takes to hit the ground is only the vertical part of the motion. We don't care about its left to right speed. If it weren't going down, it would never hit the ground. The vertical part of its speed determines how long it goes up and how long it takes to come back down. So, and then the other thing we need to know in order to make some sort of prediction for time is the acceleration, which we do know. It's in free fall because this is a very specific kind of problem that always involves free fall. So that means that our acceleration is 10 meters per second squared. We already know how high above the ground it is. So the only thing we need to know is how fast is it moving up and down right when it starts projectile motion. And to find that, we're going to use the vector solver or trig. And we need the magnitude and angle of the initial velocity to do that. And I'll go through an example so you'll see how this plays out. We need to find the initial velocity in our vertical dimension. It could be up. It might be thrown at an upward angle like this. You can throw things down too. I could throw it down like this. It will still be in projectile motion. It'll just be moving down when it leaves my hand. Or I could throw it perfectly horizontally. If I just pushed it straight out like this, then when it left my hand, its initial velocity would be all horizontal. There would be no vertical component. The vertical part of its velocity would be 0. Okay? But the vertical part of its velocity is experiencing downward acceleration. So if I throw it up, it's going to slow down and then speed up as it moves down. If I throw it perfectly horizontally, the instant it leaves my hand, it has no downward motion, but after that, it's going to be going down faster and faster and faster. And if I throw it down, then it'll start off moving down and it's still going to speed up. It's just going to keep going faster and faster and faster. If I throw it at 1 meter per second down, then after 1 second, it'll be going about 11 meters per second. because it's accelerating at 10 meters per second squared, okay? And with this information, we can find the time it'll take to hit the ground using kinematics. Once we know how long it's in the air, then we do the second part, which is to figure out how far it goes left or right during that time. Its motion isn't really in two parts. It's not going up and down and then left to right. It's moving up and down as it moves left to right, which means at the instant that it hits the ground, its projectile motion stops. It may still be moving, but it's no longer in projectile motion. It's no longer in free fall. And that at that point, it's hit the ground, and that's as far as it's going to go in free fall. It might, like if it's a ball, it might roll on the ground for a while, but that's not what we're interested in. We want to know, where's it going to land? That time that it's in the air is going to be the same as the time that it's moving left to right horizontally. So all we need to know is how fast is it going? Because now we know how long it's in the air, and we know that the acceleration is going to be 0. The acceleration is going to be 0 because it's in free fall. And free fall acceleration is straight down. There is no left to right part of it. In reality, free fall acceleration is not straight down at 10 meters per second squared. It's not 9.8 meters per second squared either. It's something different that generally depends on air resistance, which depends on the shape of the object, and if there's wind, it can depend on that too. It's so complicated that we're going to ignore it. We're just going to ignore it entirely. We may try to take it into consideration after we've made some predictions and tested them, because if we make really good predictions and they don't work out, then it's possible that air resistance is the problem. But we also, we're not going to be able to take it into consideration when we're making a prediction, because we just don't know how it's going to affect the things that we're looking at. So we're just going to assume that there's no air resistance vertically or horizontally, which leaves us with a downward only acceleration of about 10 meters per second squared. And again, we'll find that speed in that horizontal direction by using the solver. The solver will take whatever initial velocity you give it and break it into two parts. One that's either up or down, maybe it's 0, and one that's left or right. Again, this is the simplest case. So this is not the only way that we're going to deal with two-dimensional kinematics or two-dimensional anything. It's the simplest case, and it leads to problems like this. So I want you to jot this problem down while I switch into a different program, because I need it to, I need to be able to write and draw in a way that I can't do on here. Okay, so this is a projectile motion problem. It's like all problems, the numbers themselves can be different. In this case, it's launched from the ground, and so that means its initial position and its final position vertically are both 0, but it's the same. The algorithm that we use to solve this is the same, whether it starts and ends at the same height or whether it starts and ends at different heights. And what I'm going to do is walk you through the whole process of solving this problem, and then I'll explain to you at least a little bit how you might deal with it if you were taking a test and you didn't have access to the solvers, because that is going to happen sometimes. Okay, I'm going to flip. You'll still see the problem. It's just going to be smaller. So here's the problem. And we'll go through our whole algorithm, including the part of it that's dealing with two-dimensional motion. So you see, this is how we solve a projectile motion problem in 2 dimensions. And then ultimately we'll take this and we'll generalize it a little bit so that we can solve other kinds of problems as well. So the first thing I'm going to do is I'm going to draw a picture, and this is what a football looks like, as you all know. That football is kicked at an angle to the ground, so I know it's going to be in free fall. It's going to make a parabolic arc. This is going to be projectile motion. So it's going to start here, and it'll end here. What we're trying to find is this distance right here. And here's what we know. We know that it's kicked from the ground with an initial velocity of 5.1 meters per second and an angle of 34 degrees. So for clarity, I'm going to do something that I have avoided up until now, which is I'm going to use some different colors just so it'll stand out to you on the screen. You obviously probably don't have different colors to write with, but just do the best you can. So we're going to do a couple of things here that can sometimes lead to confusion. So hear me. Vectors are not arrows, and vector quantities have no actual location. However, really useful to represent vectors as arrows. And when we do that, we have to draw them somewhere. So what I do is I like to draw my initial velocity vectors as arrows that are positioned so that the tail of the arrow is where the object starts, and the arrow points in the direction of the initial motion. So that is going to be tangent to the path of the ball. It'll always be tangent to the path of the ball. This arrow represents the initial velocity of 5.1 meters per second at an angle of 34 degrees relative to the ground. This isn't an accurate drawing, by the way. This looks like this is closer to 45 degrees, but that's okay. We're not going to try to get everything to scale necessarily. And you'll see that the way this arrow points, it points above where the ball actually goes. And that's because its initial velocity vector is not constant. It's accelerating down the whole time that it's moving. So it launches in this direction, but immediately starts slowing down. So its vertical velocity becomes less and less and less. And then it starts speeding up in the downward direction. Its vertical velocity is getting more and more and more and more. We'll see lots of examples of this, but we have to start somewhere, so this is where we're starting. And then the other thing we know here is that the acceleration is going to be about 10 meters per second squared toward the ground, okay? So there's my picture. The next thing that I'm going to do is I'm going to determine my axes where the positive directions are, where 0, 0 is. So because this is projectile motion, here are my axes, up and to the right are positive, and I'm going to say the initial position of the ball is 0, 0. That makes sense, okay? So that's that whole first step of solving kinematics problems. The second step, we've skipped until now. The second step is take any vector quantities that are not aligned with your axes and break them into components. So our acceleration is straight down. It's in the negative direction in our y-axis. Our distance that we're looking for, which is an unknown, is in the positive direction along our x-axis. We don't need to deal with those in terms of breaking vectors into components. But our initial velocity is neither straight up or down, nor is it straight to the right or to the left. It's at an angle. So here's how we deal with it. First, draw a coordinate grid. And if this may seem like overkill, do it. Because as we start dealing with vectors that can be pointing in a variety of directions, this is the only way that you'll be able to keep track of whether those components are in the positive or negative direction. So draw it and do it every time. Sketch the vector on there. I try to make the angle as close as possible. So this isn't right. I didn't draw this super well. So I'll try to make this one a little bit better. This is pretty close to a 34-degree angle. And the magnitude of the vector is 5.1. Do we care what the units are? Not really, because what we're doing now is a mathematical thing that has only to do with the magnitude of the vector, not the units. And what we want to know is how much of this 5.1 unit vector at a 34-degree angle to my x-axis is just to the right, and how much of it is just straight up. I'm drawing the components in. And you can see, like, this is gonna be my X component, this is gonna be my Y component. It's gonna be pretty easy to figure out which is which once we put it into the vector solver. So let's do that. Our magnitude is 5.1. The angle is 34 degrees, and the way I drew the whole thing, it's moving up and to the right. So that leaves me with a horizontal component of 4.23, a vertical component of 2.85. So let's put those in. Our horizontal component is 2.83, and our vertical component, I already forgot, no, 4.23, I just messed that up entirely. Okay, hold tight. This is what happens when your brain stops working. Okay, let's do this one at a time because otherwise I won't remember. Our X component is 4.23, so 4.23. Our Y component is 2.85, 2.85, okay? And now, there's no more vector quantities that are at any angles, so now we just launch back into the kinematics. Well, what do? Well, because it's a projectile motion problem, and because we're trying to figure out horizontal distance from a known height, launch speed, launch angle, we're always going to do the same thing first, which is find out how long it takes to go up and come back down. That's just the vertical part of the motion. So we'll start with our y-axis variables. Initial position, final position, initial vertical speed, final vertical speed, vertical acceleration, and time. Time, which does not have a letter next to it, because time is the same in both axes. There is not a unique time that it's moving left to right, as opposed to the time that it's moving up and down. Our initial position is the ground, which is 0. Our final position is also the ground, which is 0. Seems like that wouldn't work, but it does. Our initial vertical velocity is this, right here. The vector solver told us that it's moving up at 2.85 meters per second to start with. Its final y velocity, we don't know. And some of you might be like, wait a second, this is symmetrical. It's going to be going down at the same speed. You're right, but we don't know that for sure. So we'll just leave it blank. The acceleration is down, which is our negative y direction. So it's negative 10 meters per second squared. And what we're trying to find is the time. We can do that using the solver. If you didn't have the solver and you didn't have the algebra skills to do it, you would just say, I would use these 4 known quantities along with this equation to find time. The equations would be on a test, so you don't even have to memorize those. But we have a solver that we can use, so let's do that real quick. We have 0 as our initial and final position. Our initial vertical velocity was 2.85, right? Did I mess that up? Okay. Our acceleration was negative 10 meters per second. We need to find time. We can do that with the first equation. We get 2 values, 0 and 0.57, which are both right. It's at position 0 at time 0, and it's also at position 0 at time 0.57 seconds. That's the first part. We now know how long it was in the air. Part 2 is to figure out how far it travels left to right during that time. So for that, we use our horizontal variables. It starts at position 0. We don't know where it ends. That's what we're trying to find. We do know its initial horizontal velocity. It's 4.23 meters per second. We have no idea what its final horizontal velocity is, but its horizontal acceleration, because it's in free fall, is 0 meters per second squared, which means we actually do know what the final velocity is. If you have no acceleration, your velocity won't change. So we actually do know this is 4.23 meters per second squared. It's moving left to right at a constant speed. The amount of time that it's moving is the same horizontally and vertically. So it's still 0.57. And we can use the exact same equation that we used before to find how far it goes left to right. So we don't know the final position. Our Horizontal velocity is 4.23, both at the start and the end of our time period. Our acceleration is 0. The time is 0.57 seconds. We're trying to find how far it goes, and it looks like it goes about 2.4 meters. So the answer to these questions are 0.57 seconds and 2.4 meters. That's a pretty anemic kit, by the way. That's like, 8-ish feet, like 7 or 8 feet. That's pretty pathetic. But this, according to this data, that is how far it would go. You kicked a ball sort of weakly at about 5 meters a second, it would just come up and I think 8 feet later, we'd hit the ground. So what I'm going to ask you to do after a break today is work on some problems that are looking at making these kinds of distance predictions. There's a couple of things to know. First, the first 3 are launched with a perfectly horizontal angle. That's an angle of 0, which means the launch speed will also be the x component of the velocity, of the initial velocity. There will be no y component. It's all perfectly horizontal. If you put it into the solver, you'll see that. If you put a, my mouse disappeared here. If we put a launch angle of 0 degrees in here, what you see is the horizontal component is the same as the vector magnitude, and the vertical component is 0. So you can put it in here if you want, or you can just know that if it's a perfectly horizontal launch, whatever that launch speed is the speed that it's moving left to right. And then the other thing is that this relies on you using this video to calculate the launch speed of an actual projector, and that was awfully fast. But if we slow it down, you can see that I'm just launching a ball, blue ball, from a launcher at, it's not, now it's just not working, but, oh, there it is. Okay, so you can see that it's launching, and you can just see that blue blur